End of class, we'll see. And I'm handing out homework set 6. It'll be due next Tuesday. There'll be one final assignment handed out next Tuesday. That'll be done the following Tuesday. And then the last class will be on Thursday of that week. The final exam is on Monday, 3:30 to 6:30. And I'll see if I can get us a little more space than we have here for the midterm. Right. So last time we started chapter 7 on channel capacity. It's called Shannon's second theorem, and it's the idea of how many distinguishable inputs there are. So it's usually not stated this way, actually. C is the highest rate at which you can get reliable communication, whatever that is, and so on. So, but the capacity C, or 2 to the C, let's write it this way, equals number of noise-free symbols. All right, distinguishable symbols, inputs. Or if you will, C is the log of the number of distinguishable inputs. And we talked about a DMC, discrete memoryless channel, and that consists of input alphabet, output alphabet, and probability distribution. So you put in an X and you get out a Y according to P of Y given X. Now, what kind of control do you have over Y? Think of X as an index of a distribution on Y. So this is an index family of distributions on Y, and you get to pick one. And then Y, based on what he sees, tries to determine what X is. Usually there'll be a substantial probability of error there. But if you repeat this channel many times, in space or in time, then every channel looks like this. And this is the key trick. Every channel looks like this. You put in an XN, you get a YN. The probability of YN given XN is the product of P of YI given XI from 1 to N. This is what I mean by memoryless channel. Y depends only on the current X. It doesn't remember the past X's or the past Y's. So there's no time dependence. Yeah. Then every channel looks like this. Here's alphabet input, alphabet output. There are 2 to the n h of x. We haven't proved this yet, but we'll prove it by the end of next time. 2 to the n h of x, typical inputs if you freeze p of x. That is, if you freeze the type of your code words, you'll only allow sequences x that have this empirical probability p of x for each of the symbols x. Then, each of these typical x's will give you a certain number of conditionally typical y's. I know what typical means. It means p of x super n is 2 to the minus n h of x. Well, conditionally typical just means the number that P of yn given xn for the yn in question is 2 to the minus n h of y given x. In any case, the number of these turns out, again, by our key things that we'll prove next time, h of y given x, the total number of typical outputs, 2 to the n h of y, you divide each of these fans into the number in each fan into the total number, and you get 2 to the n I of xy. In other words, you begin to see why I of xy is the channel capacity. And if you pick a subset of these at random, the fans won't overlap, which is very strange because there's just barely enough room for 2 to the ni fans. And if I'm picking 2 to the ni of these in number, let's choose 2 to the nr, where r is less than I. So this is a subset of them. If we chose them all, they overlap horribly. We have a substantial probability of error. But if we just choose a random subset of them, then it turns out the fans don't overlap. Now, that's a little strong, yes. Like what about the typical sets? Yeah, that's right. So this little bracket goes a little lower. Yeah. We're ignoring the x's that aren't typical and the y's that aren't typical. And we're getting a picture of how it works. By the way, when I say these fans don't overlap, you'd say, oh, great, he's solving the sphere packing problem. How many spheres can you put in n-dimensional Euclidean space so that they don't overlap, and so on and so forth? That'd be a special case of this. Not quite. The fans do overlap. Here's yn. But the overlap is small, so it doesn't, they act as if they don't overlap as far as the probability of error is concerned.
It is more, but is it typical? I mean, the overlapping part is typical.
No, the overlapping part's typical. It's just, remember, I chose these things at random. So the spheres, could be the same sphere. I could let the second code word and the third code word be the same. Of course, that contributes, the probability of that is so small it won't add to the probability of error substantially. Right. In fact, the early proof for 1956 of the theorem we're going to address by Feinstein used a cookie cutter approach, which I hated because it's so asymmetric. Look at it this way. Here are the x's, here are the y's. Let's look at this. This is a fan, so here's yn. So this fan has conditional probability 1 minus lambda. I just wrote 1 minus lambda in there. So lambda is your probability of error. If you send this, and you get something in here, you'll decode it as this, and otherwise you'll declare an error. Well, you'll say something else. All right, now for the next one, Einstein created 1 minus lambda content in the next fan that wasn't in the first fan. That's what I mean by cookie cutter approach. You cut this out and then you make sure that this has probability 1 minus lambda. Not the whole one, just what's left. And then you do this 1 minus lambda. You do this 1 minus lambda, and then this 1 minus lambda. And you can approve that you can get a number of these in there under this condition, which is roughly 2 to the n I. So there are 2 to the n I distinguishable inputs with probability of error lambda. And so I makes sense as channel capacity. But since I of xy, was arbitrary in the sense that it depends on the type of the code words you send, P of x, we may as well choose P of x to maximize I of xy. All right. Well, this is what takes pages and pages to handle. You know, symmetry is not to be given up lightly. As anybody who uses the Lagrange multiplier approach to solve a problem with constraints on the variables, you just add summation lambda I g sub I of vector x. You keep the symmetry and everything is nice. Later you have to find the lambdas that fit the constraints, but you've done all the hard work. Well, we also looked at the BSC with crossover probability P and found that C equals 1 minus H of P. And that looks like this. Capacity is 1 bit if there are no errors or if there are all errors. And unfortunately, capacity is 0 if there are half errors. And the reason for that, of course, is I could throw away what I receive and just substitute fair coin flips. They tell me nothing about the input here. So if P is a half, the distribution 0 and 1 is a half regardless of the input. Half a half. And at 0.11 you get half a bit through. So every 2 transmissions is equivalent to 1 transmission of a perfect channel without noise. But I'm afraid 2 transmissions isn't going to do it, although that's the interpretation of a half-bit capacity. You need 10, 20. You need enough repetitions of the channel so that the law of large numbers will give you the expectation you expect. 2 different expects there. All right, today we'll do properties of C. That won't take long. And define the operational capacity and show that this is equal to C, the information capacity. We won't show that. That's what we'll show time after this. Okay? And next time, will be